Can
Okay, wonderful. Well, good morning, everybody. So welcome to day 3. So today I'm going to deliver the first half of the session, and then after the break, Mitch is going to cover the second part. So the first part is about basic modeling and forecasting. So in this session, I'm going to cover what is a statistical forecasting, basically provide a definition of the forecasting. It's a slightly more complicated but comprehensive than the simple definition we had in the first day. And then we are going to have a discussion, and this is where I need your brain as well and your interaction. And you have been fantastic actually yesterday and day before, so we would like you to continue like that. On what can we forecast? So because there are different things that we can forecast, but are different conditions that we may need to consider when it comes to forecasting them accurately. So we need to discuss them. And then I'm going to look at some simple forecasting methods. We call them benchmarks. And then using those benchmarks, we learn how to specify and estimate models and the data, how to produce forecasts. And then we look at also what we call fitted value and residuals. This is something we will come back to it actually in day 5, because they help us to evaluate the performance of the models as well. All right, let's start by talking about the forecasting. So remember this workflow from day 1, which provides different steps when it comes to a forecasting project. We haven't really talked about the first and second step because the training or the workshop is focusing on like step 4 to step 8. But I can tell you from experience that step and 1, 2 are fundamental, and I really recommend you to not start doing any sort of forecasting if you don't have a clear understanding of what is a decision that you're going to inform by producing a forecast. And then, of course, that helps you to understand also what is the thing that you need to forecast and what are the requirements there. So in any organization, there is at least one or possibly many reasons why you need to produce a forecast. So again, I encourage you to spend a good amount of time to understand that really. So the decisions that require forecast. So for each decision that you identify, you have to also go through a certain number of steps to understand what are the forecasting requirements. So the sort of thing that we look at in forecasting requirements are, what is the forecast variable? What is the thing that I want to forecast? What is the temporal granularity of my forecast? Do I need daily forecast or weekly forecast or monthly forecast? And remember, this is different from the temporal granularity of the data available. You may have daily data, but the forecast really you need to inform a decision might be at monthly level, right? So they're not exactly the same. There might be in the same level, but in many cases they are different. And you also need to determine how long you want to produce the forecast. So how advanced you want to produce the forecast in the future. Is it for the next 7 days? Is it for next 7 weeks? Is it for next 6 months? Is it for next 12 months? Is it for next 10 days? For 10 years? So whatever horizon is, you need also to determine that. Another thing that you may think about here is how often you produce the forecast. Do you generate the forecast every month? Or no, you generate the forecast at the end of this month for next 12 months, and next time that you generate the forecast is going to be after 12 months, okay? So in this case, the frequency of generating the forecast is 12 months. In the first case, the frequency is 1 month because you generate the forecast every month. So these are some important things to consider before going to like the detail of looking at the data, preparing data, visualizing them, and then the rest of this workflow. So I think this is really important. So I want you to spend few minutes. So I will share actually a link on Padlet here. I don't know whether you have used Padlet before or not, but it is really simple to use. So I shared the link. And then what you need to do is you need to tell us what you think. So here is the link in the chat. So if you click on this link, right? So you should be able to see something like this page. Okay, and then I want you to click on this plus here at the bottom. And then you'll see a window like this. I want you to type a decision. And again, this maybe is related to the sort of work that you do, depending on, which area you're working on. This might be different. For instance, a decision, if I'm working in a hospital, the decision I want to inform by my forecast is determining, something is wrong here. Determining the number of doctors and nurses.
Sorry, Baba, we can't see your screen. What you are showing us, we can't see it.
Okay, thank you. This is something I need to double check then. Do you see it now?
Yeah.
Okay,
Yes.
so yeah, exactly. So here you type a decision. So how many doctors and nurses we need in a hospital? Let's make it like that. How many doctors and nurses required in a hospital in the next 42 days? So that's the decision I want to inform by forecasting. So here I want you to think about something like that. So this is my example, my decision. So think about the decision, and then here type what is the forecast variable. Well, I have to forecast. There might be also many things that I need to forecast, but one of them is hospital admissions. Forecast granularity, well, is day. Forecast horizon is 42 days. And then forecast this frequency could be also sometimes misleading because it is used for many things actually in forecasting. But here I'm talking about how often we produce a forecast. And then here it is also 7 days. Okay. So there are actually other things that we need to consider when it comes to determining forecasting requirements, but these are the most important thing. And when you have done it, just click and publish, and then you will see it here. So let's see how many examples we get. And as I said, this is something we don't really spend, time on it, but it is fundamental. It's so important to get the decision right, because if we don't know how the forecast is going to be used, well, there is no value really to invest your time in producing a forecast. So that's why it is important to understand the decision. But that helps also to make sure the amount of time you invest in producing a forecast is in the right thing. Is the right forecast variable, is the right granularity, right horizon, right frequency, and so on. And actually, this has a lot of implications in terms of the modeling, how we model things, how we evaluate the quality of the forecast, and so on. And this is also somehow domain specific. So that's another reason why we don't spend a lot of time, but I just want you to give this opportunity to have a 10 minutes, think about this, and then we can move on. Well, someone copy and paste exactly what I did, I think. But the idea is to provide your example and not just copy and paste my example. So we have an example. How many students will complete their undergraduate studies? Okay. But again, and that is a very good example because it's very typical. Basically here, you're confusing a decision with a forecast variable, right? Because you want to forecast how many students they will complete the undergraduate studies. That's what you want to forecast. But you do this forecast to do what with? That's the decision that you're going to inform. So this example is a typical example of sometimes, we confuse a forecast with a decision, but a forecast is different from a decision. The decision is something that we make in the light of the forecast. For instance, if you work in inventory management, you may forecast the demand. So how many products you will sell, or what would be the demand for your product. And in the light of that, you may make a decision how many products you want to keep in the shelf. Okay, so these are not the same. These are two different things, and you need to be careful to avoid confusing a forecast with a decision. Again, how many students will successfully complete the PhD program is the same. It is the same sort of typical mistake. And another important thing that I want to highlight here is this forecast granularity. You provide it as 10 weeks, and then you say forecast horizon is 6 months. You need to remember the granularity should be the same, otherwise it will bring further confusion. So if you say the granularity, first of all, granularity cannot be 10 weeks, except if you have really the periods of 10 weeks, which I don't think this is what you mean. So forecast granularity basically refers to temporal granularity. In Tissable, if you remember, there is a square bracket that tells you 1D, 1M, 1Q. Here, we refer to that, basically. We talk about that period. Is it daily time series? Is it weekly time series? Is it quarterly? Is it monthly? That granularity refers to that. So these are really interesting examples, and it shows why it is important to think about this more. I think this how many road traffic injuries will be reported in the next 24 months, and the forecast variable is RTI associated. I'm not sure actually what is this, but to me, it seems like the road traffic injuries are also the forecast variable. They are not the decision that you're going to make by that. For instance, this how many healthcare workers are required for vaccination in the region for the next 3 months. Again, the decision is right. So you need to identify how many workers you need, and based on this, maybe allocate people with workload and maybe schedule them. And then what you need to forecast is the number of vaccines available. You want to forecast it every day. If you want, I prefer you provide the forecast horizon as day as well, because if you want to forecast every day, it means it is likely that your forecast horizon is daily as well. So you provide 90 days instead of, I think you just Yeah, so more examples are coming. I just missed that one. Yeah, so that 3 months, you should make it 90 days, something like that, if this is what you want, because you cannot have forecast granularity at daily and then forecast horizon for 3 months. So maybe people understand you, but it is better to be clear, 90 days. And then forecast frequency, 3 times. So again, there is a bit of like confusion there. So I'm not sure if you forecast 3 times in a year, 3 months, so you wouldn't forecast for the entire year. But again, this is something to reflect on. Yeah, so I think this example are brilliant, really, but it highlights a very sort of common mistakes, which is fine to make. But I just want to highlight this important topic. So you need to understand the decision clearly, the decision that you need to make, and to make the decision in the future, you need to have an understanding of a forecast of something, an estimation of something, right? I want you really to think about this too. These are different things. These are not the same. And these examples, I think there are examples here, they are correctly mentioned this, but also there are many examples where they confuse a decision with a forecast. These are not the same. These are different. So make sure you spend some time in your work understanding this too. You should be crystally clear about how the forecast you generate is going to be used and what is the decision that the forecast is going to inform. Because remember, at the end of the day, we do all these things because we want to make decisions, and then following that, we start planning, right? So basically, the planning is a response to the forecast you generate, the decision that you make in the light of the forecast. Maybe you have also target in the organization that you want to achieve that will affect, of course, the plan. So the plan is really a response to the target you have, the decision that you make, and also the forecast that you generate. So you shouldn't confuse a target with a forecast and with a decision. These are different things. All right, so I think we can now go back to, and we are going to have this sort of discussion in Padlet, in other sort of platforms as well. You can keep actually typing later if you like. I'm happy to share this output with everybody there, and we can discuss more later as well. So let me go back to my slides. Please let me know if you don't see the slides. So I have to change maybe the screen. Do you see the slides?
Yes, we see them.
Okay,
Yes,
wonderful. So step 1 and 2, we haven't covered many things, but I just wanted to emphasize how important they are. Now, so in day 1 and day 2, spend really a lot of time understanding how to prepare data, and this is where you use Testable. So Testable is a package and containing many functions that help you to prepare data for understanding, but also forecasting. And you have also learned using many type of time series graphics, how to visualize data. And there are 2 main purposes to do that. One is to understand the data, basically to see whether there is any pattern like trend, seasonality, autocorrelation. Is there any peak in your time series that might be affected by an event? So it also, that highlights maybe you need to go back to step 3 and collect certain data that would be useful in building the models. So that's one purpose, that actually we try to understand the data to see whether the time series that we are dealing with is easy to forecast, it has patterns or not, and whether we could collect more data that could be helpful in building models. Often, time series are affected by many events. So, for instance, the vaccine data that we use in the apply exercise, so the consumption of the vaccine or dose administered in that case is affected actually or is driven by population, but also is affected by strikes. So there is a strike in the data that affect the those administrated. So without looking at the time series and visualizing them, we don't know actually that information. So this is how I realized there is something affecting the time series. I asked people with domain knowledge, what is that? And they helped me to collect more data. They told me actually that there was a strike in that period. So I collected more data, and then we used this to build a model with later. So we covered these two main things. And the purpose of today is actually to focus on step 6 and 7. So we learn how to choose and train models, or how to fit and estimate models. So we learn how to use Fable package to specify models and then train them on the data, and then how to produce forecasts. And when it comes to models, today we just look at very simple methods. Tomorrow we cover exponential smoothing and ARIMA, and actually this afternoon we are covering also regression models. And in Friday we cover step 8, which is evaluating quality. Okay, so these are the steps that we go through in statistical forecasting modeling. So we prepare data with Testable, we visualize data with FIST, and you can use ggplot2 for that if you like. And then we choose and fit models. So we specify the method and train them on the data, produce the forecast, and evaluate the quality. So there are other steps, but we don't cover the other steps. These are the main steps we go through in the statistical forecasting. So now, what is a forecast? You remember in day 1, we had a definition of a forecast is a genuine estimation of a variable about the future. So estimate something in the future based on all available information that we have at the time when we generate the forecast. Well, this is a really nice, simple definition, but I want to provide another definition that probably it sounds a bit more complicated, but it is more comprehensive. So we can think of a forecast actually as a random variable, and then we define a forecast as an estimate of a probability distribution of that variable that we observe in the future. So if you are maybe in the field of statistics, so you may have an understanding of this better than others, but if not, don't worry, because I provide an example for this. So this is the data set of short-term visitors in Australia. You had to look at actually yesterday in tourism data. It was a quarterly data set. This data is monthly data set. So in y-axis you have thousands of visitors, in x-axis you have months, and then now you are a kind of expert based on what has been covered yesterday. So you can actually get an understanding of the sort of pattern we see here. We have some consistent pattern that repeats every year. And then there is a sort of like increasing trend here as well. So based on this pattern, I can apply a forecasting model and then produce a sample path or one possible future. So here we use exponential smoothing. We cover this tomorrow. So again, here the concept is important, how ETS is working. We will learn about this tomorrow. So we apply the exponential smoothing model on the historical data in black line. And then this method actually, in addition to capturing trend and seasonality, can also get an input of randomness. So by having that, we are able to produce one possible future. And by changing that input, which is the randomness, we can actually generate another possible future. And by getting different samples, we can get different possible futures. And we can produce 1,000 possible futures from this. And if you do this, we have a pretty good understanding of where the possible future may lay down. We are not very sure, like 100%, that it is going to be exactly in that path, Of course, the reality is going to be just one path, but we don't know about it. And that's one important thing in forecasting, right? Forecasting is about the future, and future is uncertain. If we knew the future and it was certain, well, what's the point of doing the forecasting? So, and that's a really important point. So when it comes to forecasting, we need to acknowledge uncertainty in the forecast. So this will provide us with a possible future, and then if you bund them together, you see this as all the possibilities. And if we take an average across this, all possible futures, we get this blue line. And this blue line is something that we call it the point forecast. So point forecasts are single number estimations. So I say the visitors for next month, they are going to be 500,000. So it is just one number. That's the point forecast, and we represent it as this line. These are the points in each month, and we link them together. So in addition to that, we can also have intervals, right? So we can zoom in a little bit to actually see this better. So there are all those like future paths, but we have the point forecast, and there are two intervals. So this blue like area, this is a 50% prediction interval. So we have a coverage of 50%, and another one is 80% coverage, right? So we can get all the possible futures, and from that we can get the point forecast. We can also extract prediction intervals from it. I think I want maybe to focus on this more a little bit, what we mean by the probabilistic forecast or forecast distribution. Because we generate many possible futures, we can actually in each month, so remember, in each month we will get 1,000 possible futures. So if your horizon is 48 months, for the next 48 months, for each month you get 1,000 possible futures, and then you can create a histogram of it, something like this. This is not exactly related to the previous example, but I just wanted to show you the idea of how we can visualize the distribution of the forecast in different horizons. It could be day, week, months, etc. And then when you have the distribution, we can get basically anything from it, including the mean of the distribution, which is often the point forecast we're referring to, but also any interval, right? So this is one way to represent the forecast. Of course, we could have a density plot here instead of the histogram that I created here as well. And this is what I want to show you here. So when we talk about the forecast distribution or probabilistic forecast, basically we are referring to something like this. So you will have a distribution for each period in your time series, right? So if you forecast a quarterly time series, so for each quarter in the future, you will get a distribution like that. And this distribution gives you a comprehensive view of all possible outcomes for the variable that you want to forecast. So here in this x-axis, you will see the possible outcomes for a potential forecast variable. And then in y-axis, you see the density. So you can extract the point forecast from the distribution, which is the center. You can also extract the prediction intervals, which is the area that you see under this curve here, right? And you can extract actually any quantile if you are interested in the percentile or quantile of a distribution for your decision making. You can extract it from here as well. So now, of course, there is a difference between a point forecast, a prediction interval, and an entire probabilistic distribution. So my question for you would be, what is wrong with using only the point forecast? If you want, you can put your answer in the chat. So what is wrong if you produce a forecast to inform a decision and you rely only on the point estimation? So there is a question about, are these futures based on scenarios? Well, one interesting thing is, these are the possible futures are based on different sampling that we get, from the residuals, and we talk about the residuals. What are these residuals? But they just introduce randomness to the forecast that we have. They are not really scenarios, but what I want to mention that is related to scenario is, when you have the distribution of your forecast, it has everything that you need, including those scenarios. For instance, here, depending on the area that you work at, you may call it this left-hand side of the distribution. You may call it worst case scenario or best case scenario, for instance. Okay, so if you are in retail industry, this side is worst case because you're not selling well. Actually, the right-hand side is the best case scenario because you're really selling well. If you are working in a hospital and you have a distribution like this, so the right-hand side of this distribution, this tail here, actually is related to worst case scenario, because it means you get a lot of patients in the hospital is under pressure, you cannot provide a good service. But the other tail in left-hand side is the best case scenario for hospital, because they're happy, they don't receive many patients, so there is no pressure, they can provide good service. So the scenarios that you're talking about, they are embedded in the probability distribution of the forecast that you produce. Yeah, so you mentioned something like confidence interval. Again, I think you referring to prediction interval. The confidence interval and prediction interval are not the same. They are slightly different. So here we talk about prediction interval, not confidence interval. Yeah, so the point forecast is just like a best guess, is the expectation. So the future wouldn't be exactly that point. So it will deviate from that, depending on, again, the variable that we forecast. So if you make decisions based on that, and because the point forecast is just one single number, it doesn't tell you anything about uncertainty. Right? So if you make a decision based on that, that decision wouldn't be a good decision. So a point forecast provides an illusion of certainty. So when you provide point forecast to people, immediately they take it as reality. They think this is going to be that. So it is really important to tell people also, well, I give you a point forecast. And again, remember, the point forecast is what you see here in the middle of this distribution. In many cases is mean of a distribution, sometimes could be median. So they are center, but here we have many possible outcomes. And these outcomes, they have different probabilities of happening. Okay, so point forecast alone, they are not good because they don't give you information about possible future, and then they don't acknowledge uncertainty. So I want also to tell you why prediction intervals are helpful, but again, doesn't give you more information. So the point forecast is single number. I tell you I have 500 patients in my hospital next week, and then I can give you also an interval. Well, I say with a 90% coverage, you may actually receive probably 600 or 400, so something between 400 and 600. Now, what is important is the probability of different outcomes between 400 and 600 are not the same. Okay, as you can see here, the probability of something happening here is different from the probability of actually something happening higher. So even if I look at the interval, I give you just two numbers, the number that you see here, the number that you see here, but different outcomes within this interval, they have different probabilities. Some they are more likely to happen, some they are less likely to happen. Well, there is no difference between point forecast, point estimate, and point predict. Again, these are different terminologies people may use. Here we use the term forecast. Some people may use predict. But in general, when we talk about forecast, we talk about time series. So you have a data that has been stored in the past. You're going to use it to forecast the same variable in the future, but also you have information about different predictors like strike, population, temperature, and this sort of thing. What is important is the point forecast is one single number. The prediction interval gives you a range with a coverage, so 95%, 90%, 80% chance that the actual lies in this interval. So you need to be aware of the limitation of each. This doesn't give you any information about uncertainty. This provides some information about uncertainty, but it doesn't give you information about the likelihood of possible outcomes. All right. So now we have a good understanding of actually what a forecast is, what we are expecting to get as a forecast. So depending on, again, how you do it, sometimes you may just rely on point forecast, sometimes prediction interval, but our recommendation is to go for the forecast distribution if you can. If you can, at least provide the prediction interval. And actually we learn how to do it, how to create all this later. I'm trying to see how I can get rid of this, I think, here. So you'll learn how to produce the forecast in the next couple of minutes. Okay, so some notations. So the thing or the variable you want to forecast, we use a notation of yt plus h. So h here refers to the forecast horizon. Capital T refers to the total number of observations. So it refers to basically the last observation that you get in a time series. So we know the observations from period 1, so 1, 2 up to period t, and then we produce a forecast distribution. So we are interested in the distribution of yt plus h, and remember h changes from 1 to 2 to 3. So if it's 1, it refers to the next period. And again, remember the period, depending on the time series that you're looking at, could be day, could be week, could be months, could be quarter, etc. So interested in yt plus h given t, so it means we know all this information, and we are interested to get a distribution for that. The point forecast is just the expected value of that distribution. And we can also have the variance of that distribution. And again, the variance refers to the dispersion in the distribution that I showed you. If it's centered, it's closer to the center of the distribution, the variance is lower. If it's dispersed, the variance is higher. And then the prediction intervals is the range of values with the coverage that we can get from the yt plus h. And I think this actually slide summarizes well what we can get or extract from a forecast distribution. All right, so now we have a good understanding of actually what we're expecting to produce as a forecast. Now, let me show you one interesting example of the previous forecast that we generated here, right? So because the time series that we are looking at, it has some systematic information, and the forecasting method that we used was capable of capturing quite well, actually, those systematic patterns. But I haven't plotted the actuals here, but I plotted here, right? And if you can look at the actuals and the point forecast, up to here, is doing a decent job, the model. It's quite close to the point forecast, but most of the time is within, I mean, the 50% of time is within the, almost 50% of time within that 50% prediction intervals. So, and that's what we expect from that interval. But then something happened, and that was COVID-19. And of course, because of that, there was actually no one visiting Australia. We couldn't actually visit anywhere. So the model is still predicting a sort of similar patterns, because that's what actually we do in forecasting. In forecasting, we are interested in systematic information like seasonality, trend, level, autocorrelation, and we want to use them, of course, with also predictors to build a model, right? And this is what happened. So this model, ETS, captured the systematic information, trend, and seasonality, and used them to forecast the future. But at this point of time, so up to here, future and past were similar. It doesn't mean they're exactly the same. It means we observe this consistent patterns that we have in the past, we see them in the future as well. So we had actually that assumption that was valid. So up to here, the future and the past, they were similar, but something happened here, COVID-19, that made it, the future was no longer similar to the past. And that's why the forecast failed here. The model actually couldn't deal with that simply because it didn't know about that information. In the historical data, we didn't have such information. So if the model doesn't know about something, if it is not included in the data we use to train it, it wouldn't be able to provide a forecast that is reliable there. So that brings an important question of what can we forecast? Well, of course, we can forecast almost everything, but the question is how accurately we can forecast. So we can forecast the different things in the stock market. We can forecast, some people may do currency exchange, the pharmaceutical sales or the consumption of different products. Vaccine could be a part of this that we have in our apply exercise. We may also forecast electricity demand. This is something we are familiar with all. The temperature in different places. This is probably not what we do really, but again, it's something we see very often. Time of sunset or sunrise. Again, this is something we may take it for granted, but this is a sort of forecast really, is quite accurate. And then also some astrological events like the time of comet. So here is a list of things. I think the pictures I showed you for this. So my question for you is, what is easiest to forecast here? And of course, this question brings another question, which means how you measure it. Mitch covers features yesterday. Actually, features can help you. There is a feature that helps you with forecastability to tell you how you can measure, which is a spectral entropy, but you can also use something like a coefficient of variation. That's one question. And another question is, what makes something easy or what makes something difficult to forecast? So now I'm going to share a poll here. And let's see if it works. So what you need to do is you need to rank from easiest to most difficult one. So from the list, again, you should see them there. Okay, if you don't mind, please click on the link. And then you have to start ranking what you see there. What is the easiest? what is the most difficult one to forecast from that list? This is the first time actually I use this ranking thing in the Mentimeter. Hopefully it is going to work. So this is not my order, like I haven't ordered them based on easiest to or the most difficult one, but I want you to do it. And depending on how many people vote, we can get an idea of what is the easiest, what is the most difficult one to focus. And as you do, you know, think about, okay, what makes this easy? What makes the other one difficult? Why you think this is easier? Why you think the other one is difficult? Okay, we have 6 votes, but we need more votes, please. Let's get at least, I think we should be about 37 participants. So we need at least 30 votes. So let's get 30 votes, please. Still in 7. Okay, 10. Okay, 19. Can we get more? Ah, that's changing now. So time of sunrise was first, now it came second, which is interesting. What is interesting is timing of next Halley's Comet appearance, which is almost everybody believes is the most difficult to forecast. Again, these are the different type of forecast. I would say this is not something at least I do. Okay, 26. If you get 4 more, then we can move on. And then we can discuss briefly what makes something easy or difficult to forecast. Wonderful. One more. Well done, everybody. Let's get that one more, because my target was 30. And that means we still have a couple of people. haven't participated. Can we get one more? Well, okay. Okay, someone is still, I think, doing, so changing things there. Okay, well, it seems like we wouldn't be able to get that one to hit the target. But this is really interesting. I think I agree actually more or less with this ranking, except the last one. So the last one, I will put it quite higher, like similar to time of sunrise, because we can actually get we know when would be the timing of the next comet appearance. These are astrological sort of thing that we know with kind of certainty. There is less uncertainty around it. But I think for the rest of this, I agree with more or less with what you have provided there. The most difficult one would be probably the Google stock price that comes in 6 months. Oh, well done. Okay. So we have the 30, you had the target. Now, if I go back to my slides, so very briefly, what actually makes something easy or difficult to forecast? Well, first, and this is really important. So again, before embarking into producing the forecast, reflect on this. Because I have seen people, they have 2 data points, and they want to forecast for next 30 months or next 3 years. So that makes it 36 months. Well, you cannot do that with 2 data points or 2 months of observations. You want to forecast for 36 and you want to use a statistical forecasting. It is not really a good idea. So it is important to reflect on this. And this is not a comprehensive list, but you may have some other elements, but these are some of the most important ones. So first of all, if you are dealing with the forecasting variable and you have a very good understanding of the driving factors of that variable, so what contributes to variation in that variable, and whether you have information about that, there is a chance that you can provide an accurate forecast. So that's one important thing. Do you know the driving factors or not? The second thing is about data availability. If you don't have any data at all, it might be difficult to do it. If you have a lot of data about forecast variable, it is likely that you can produce a good forecast. So another thing is whether the thing that you forecast is affect itself. Probably the currency exchange is one example. So if the thing that you forecast will affect its outcome in the future, it is probably not easy to get it right. Another important thing is about how much variation, like randomness or noise, you have in the data. If you are dealing with a variable that is dominated by noise, well, you cannot do much actually when it comes to forecasting, because forecasting is about using systematic patterns. The time series is dominated by noise. Well, probably the best thing you could do, depending on what you forecast, would be a very simple benchmark that we cover later. And another important thing is whether the future is similar to past. So the sort of patterns that we observe in the past will be observed in the future as well. And as I show you in the example of visitors in Australia, that was not the case. And that's why the forecasting failed. So these are some factors that you need to think about, which are related to forecastability of a variable before embarking into the modeling part. Okay, now, so we have a good understanding of what we expect the forecast to be and what are the factors that contribute to its forecastability. Now let's go actually through the step, is it a step 5 and 6? So choosing and fitting models and then produce a forecast. So, and we do it using Fable package in R. And Mitch is one of the main developers of the package, if not the only one. So it is great to have him here, so we can ask him any question about Fable. So, but to be able to actually do that and show you how we specify and estimate or train models on the data using Fable, I need to introduce you first with some simple methods that we call them benchmarks. So these methods are really simple, but there are always a reason why we consider benchmarks in our forecasting toolbox. At least there are two reasons. The first reason is actually, surprisingly, sometimes these extremely simple benchmarks could produce very good forecast, depending on what you forecast and what are the systematic information. And the second thing is, or second reason why we have to have benchmarks or simple methods, is because if you invest your time in building a forecasting model and you cannot show that that model provides more value, whatever value would be, one dimension that we look at in terms of the value is forecast accuracy. So if the model that you built recently with AI, machine learning, or regression, whatever, cannot be better than a simple model, then what is the value of investing your time or telling people I have a new model? So you have to really use a benchmark in all forecasting tasks you do and show people that you do at least better than that. So benchmarks are simple models. Sometimes benchmark actually could be a current model you use in the organization, right? So maybe, it is actually the case in vaccines. So in vaccines, UNICEF or WHO, they have a forecasting model, right? They use to forecast the doses administered and needs for vaccines. So if you create a model, you should be able to show that the model you produce or you created is better than the existing model. Otherwise, no one actually would buy it. So what are these simple models we look at here? Well, there are some examples that you have seen yesterday. So you may have an idea of what sort of model actually would be suitable for this. So this is the Australian quarterly beer production. If you remember yesterday, so there are some systematic patterns, so consistent pattern that we see in this time series. So if we deal with time series like that, a method that we use should be able to capture this information. The number of pigs sluggers in Victoria. This, I'm not sure whether we look at this time series or not, but again, you may see some systematic information here or not. So this one is a yearly data. We have the Facebook closing stock price in 1 year in 2018. Again, you may tell me there are some systematic information, but what is the method that you use for this? So the understanding part, which comes from the visualization, may give you some ideas. It might be right, it might be wrong, but remember, sometimes as human being, we actually see rabbit in clouds. So we see patterns where they don't exist really. So let me introduce you with simple models then, simple methods here. The first method that we introduce is called average. And well, what this model does, it goes and look at the entire historical data, and it takes an average and use it as a forecast for future. And here it produces only point forecast. So that's why we see just a line here. So again, you remember that notation. Whenever you see a Y hat, that refers to an estimation or a forecast. And here we're talking about T plus H. It is our horizon, given we have the information from the first period to the last period. So we take a simple average of it, and that would be our forecast. As simple as that. Arguably, even a simpler method is naive method. So what naive does, it goes and takes the last observation available in the time series and use that for any forecast horizon that you want to forecast. So again, it doesn't really capture any trend, any seasonality, any pattern that we have discussed before. It's just the last one. And yesterday we discussed that this could be possibly, if you forecast the stock market, this would be possibly one of the most accurate actually model for stock market. And another similar method to naive is seasonal naive. So here, instead of taking the last observation, we go and take the last season and we repeat that over any number of horizons that we are interested in. So if you forecast the monthly time series data, if you want to forecast for next January, you go and look at the value of the previous January. If you want to forecast for February next year, you go and look at the value of February in the previous year, and so on. Okay, so here we have a seasonal period M, and this refers to that fixed period of time we talk about in seasonality. So in monthly, M is 12, in quarterly, M is 4. If you deal with daily data, one possible option would be 7 days. So seasonal naive looks at the previous season. So that's why we have something called leg M. It means how many legs I have to go back, or how many observations I have to go back. And then we can have also drift. So drift basically it takes the last observation, that's what we have in YT, and then it adds the average changes, right? So we calculate the changes, and we have T-1 observation because we cannot do that calculation of changes for the first period. So we get T-1. And if you do some simple math, you can show that this and this, actually, they are exactly the same, right? Because they cancel out each other here. So, and this H is for H possible future, the forecast horizon. So it is like extrapolating a line from the first observation to the last observation, and then continues like this for the future. So these are 4 simple methods that we use today, but from this afternoon, we learn more about them. Okay, so we need to know these forecasting methods to be able to go and see how we can specify and train them on the data using Fable. So, and this is what we are going to do. We have started looking at that actually yesterday with the STL, if you remember. So the first thing we do when it comes to applying a forecasting method into a time series in Fable in R, that's what we do here, is to learn how to specify a method. And here, similar to base R, we use a model formula. So in the model formula, we have the response in the left-hand side. This is basically the forecast variable. This is the thing you want to forecast. You have a tilde, and you have terms in the right-hand side. And these terms could be different things, could be some specific functions for each model. Each model, they may have their own functions, like trend, seasonality, or we may have also predictors here. So now one important thing, every model that we use in Fable, right? Every single model, it has a name, like every other functions in R. Now, when it comes to the name of forecasting methods in R, they are in capital letters, right? So, for instance, S-naive, this is the name for S-naive method that we just discussed. And remember, they are in capital letters. So this is one important thing to remember when you specify methods in Fable. Here is a sort of like a template that we use to specify methods and also train them. So let me tell you how we do it first in terms of specifying. When it comes to specifying methods, you need to remember what is the name of the model 1 that you use, what is the name of the model 2, model 3, model 4, etc. Here, you provide a name yourself. Choose underscore name 1, whatever name you want to prefer. It is your option. It is your choice. Okay, you put a name there, equal the model that you want to use, a parenthesis, and then the variable that you want to forecast, tilde. If you have terms, you provide a term. So if you have multiple models, you provide the comma, and you go to the next line. All right, so what happens is this. I have my data. This must be in a testable format. We have already learned how to do it. And then I use a pipe operator. I pass my testable data to a function called model. So what is the purpose of this function? It goes and trains the models that we specify here on the data. Okay, and when I run this, because I save it here with this assignment, I put it inside my underscore Mabel. Basically, it creates a new object. It returns a new object that we call it Mabel or model table. So this is what you need to do to specify and estimate models on the data or train models on the data. You can use this template. Now, let me show you an example. Here we have the Australian dataset, the Australian production dataset. We have used it before. So house production, we pass it to the model. These are the names that they have been given to this. So, I mean, we use this because of actually that operation, but we could do something else anyway. So there is a name equal. This is the model name for seasonal naive method just we introduce. Here we have the response variable, which is a column in the house production. And then a comma, go to next line, a new name for the naive method. This is a function for naive method we just introduced. The beer is the forecast variable or the response. And then for the drift, we use a function called RW, which is for random walk. And then it has now a term called drift. So basically, as we introduce, more methods, you will learn what are the possible terms that you can use in each method. And then finally, here we have mean. So this is a function for the average method that we introduce at the beginning. So now if I run this, and then I assign this to beer fit, and I observe beer fit, I will see this as output. And this is the model table or Mabel. Now, what is important here is this. You need to know that in Mabel, we have columns corresponding to the models that we have here. So I have 4 methods and I have 4 columns. So each column corresponds to one method that I specify here. What about rows? Each row corresponds to one time series. So here I have 1 time series, I get 1 rows. If I have 9 time series, I get 9 rows. And what is this? Well, this is an object, and inside this, there are some information hidden about the fitting. It could be estimation of the parameters. It could be information about the value of the estimation, which is fitted values, the difference between fitted values and actuals called residuals, etc. We learn how to export the information from here. So this is basically one of the most important things we need to know, how we specify methods and how we train them using model function. So these are the sort of functions that you can use to export information, hidden inside this. And we do this more later in the exercise function. So, but you need to note this report, tidy, glance. So these are the functions that help you to get more information about the model specific parameters and other sort of coefficient information hidden inside it. So you'll use them later with ETS, regression, ARIMA, but also in the exercises. So now we specify and train models, so we can check the performance, but this is the topic of day 5. So we'll come back to this, how we check performance of this model. So the next step is to produce the forecast. So how we produce the forecast using a function called forecast. And this function takes an argument inside the parentheses called h, and this h is related to forecast horizon. Depending on the model that we use, if the model has predictors, instead of H, we use something else, but we will learn it later in the exercises, but also in the regression part. So what we do then to produce a forecast, we take the Mabel that I just created and saved, and with a pipe operator, I pass it to forecast function, and inside parentheses, I put H equal. So here, you can either provide this as a plain English, right, as inside quotes, or you can provide a number. If you provide a number, the number corresponds basically to this interval. So if you say 5 years, so here it means you are actually forecasting for 20 periods because it's quarterly. So if you can either provide H equal 5 years, or you can provide H equal to 20. So that means it is going to be 20 quarters ahead. So now here are some really important stuff as well. So what we see inside the beer fit, this is something we call it a forecast table. So it is like a table, as you can see, with rows and columns, or fable. So fable is the object that we see here. So here we have a column called dot model that corresponds to the list of the models that we specify and train. And then you have a column called quarter. This is our index. We had it in Tessable. Now we have two new columns here. One is the name of the response variable. And here we see basically the distribution. So for each method and each period, I get a distribution. And then I get also what we call here, so that mean here means the point forecast, right? So this is the average or the mean of the distribution, and this is the variance, right? So for the probabilistic forecast distribution, this is what actually have. So we have a column corresponding to that, and we get a column also for the point forecast. We can visualize this as well. So we take the fable or forecast table, we can pass it to autoplot, and then here we put the data that we use to create a fit or the Mabel, and also later produce the forecast. Here there is one argument called level equal null. So if you put this null, it means you don't want to see prediction intervals here, and that's why I see only the point forecast here. And then we can also add some like labeling to make it nice. So you can visualize the forecast if you like. And it seems like the seasonal naive somehow is similar to what actually we see in the actual data. That we cannot say it for sure. We have to go to day 5 and learn how to evaluate the accuracy. But it seems like it captures that it might be the method that is suitable for this time series here. Okay, so the forecast distribution that we discussed could be actually generated in 2 different ways. Either is based on an assumed distribution. So here, in many cases, and in Fable, we have this as well. So we assume that residuals are following normal distribution with some other assumptions about the residuals, which we discuss in residual diagnostic again in day 5. So based on this assumption, we can produce the forecast distribution as a normal distribution. So we need to estimate the mean and the standard deviation of that distribution over the forecast horizon that we are interested in. Of course, there are other possibilities to produce the probabilistic forecast, and depending on other methods that you may have, I think in Fable, Mitch can correct me. So most of the distribution that we forecast is based on normal distribution. I'm not sure if Fable TS count is, I think you can produce forecast using Poisson and negative binomial there as well.
Yes, that's correct.
So in terms of the forecast distribution, for the simple methods that we discuss here, actually we can even mathematically show what would be the distribution over the forecast horizon that we are interested in for mean, naive, seasonal naive, and drift. Again, it's based on the assumption of residuals are following normal distribution. So we can even mathematically show that. And you don't need to be worried about this because everything here is embedded into the functions in Fable, and automatically they produce this for the methods covered actually in the training. So now if you tell me that the normal assumption that you have for residuals is not really a valid assumption, well, you can still use another approach to produce probabilistic forecasts, and that is called bootstrapping. So it's a sort of like a sampling approach. And that's actually what I did initially. When I introduced what is a forecast, I produced different possible future, and I did it using bootstrapping. So bootstrapping is going to sample from the residuals in the past randomly, and by sampling and adding it to point forecast, and then regenerating the forecast and sampling again, by repeating this step, it creates many possible random paths or many possible futures that we saw initially there. So how we can do this, how we can produce possible futures using bootstrapping, we can do it using this function called generate. Okay, so we take the same tessable, we just do some transformation here, we filter, focus on one part of this, right? And then we select just beer from aus production. And then we have our data, we pass it to model, and then we specify the method. So we get our Mabel here, and then we pass the Mabel to a function called generate. We have to provide the horizon. Here we provide how many times or how many possible futures you want to produce a forecast for. So here I provide 5. You can provide 1,000 possible futures. One thing that you need to be aware of is the computational time. So one disadvantage of the bootstrapping is it could be time consuming depending on how many time series you have and you run. And so this bootstrap should be also true to tell that we actually using bootstrapping. So if you do that, so here we get something similar to what we had before in the Fable, which is actually in the tessable structure here. So we get dot model, which is a list of our models. Here you have a new column called dot rep. So it tells you that replications is 1, 2, 3, 4, 5, up to any number of times you produce. And then here you have the quarter that again is our index, corresponds to the number of periods you produce the forecast. And then you have dot sim, basically these are possible futures. And this dot inov is the sampling from the residuals that I mentioned. So each time we take something randomly from it. So dot sim is actually what we need because this has all the possible futures here. So this is, if you visualize it, for that 5 that I generated, this is what actually we see. We see those 5 possible futures, but you can produce, I mean, I don't think there is an exact rule, but something like 500 to 1,000 possible futures would be, I think, what you could use. Well, this is also embedded directly in the forecast function as well. So instead of going through the generate, so something is missing here, it should be a forecast. So in the forecast function, you provide the horizon, and then you say bootstrap through. Automatically, it's going to use bootstrapping. And it gives you basically the sample distribution and also the point forecast. So if you want, you can also do it with the forecast function directly. You can also extract prediction intervals from the Fable. The function that we need for that is high-low. Okay, so we have our Fable or forecast table. We pass it to high-low. We say what is the level of the coverage you want or the prediction interval that you want. And then you can actually unpack that. So if you just do that, you will see it for one as one column. But if you want to have it a different column, so you use this unpack hilo and you put this name inside it, and you will get two columns for lower and upper bounds of prediction interval. So you can extract that if you like as well. So you can also actually get multiple levels at the same time. You can provide a level as a vector. So any sort of level that you want, you can also get it from there. So if you do that, I haven't actually used it with unpack hilo, not sure whether that works, but if unpack hilo doesn't work with two of them, if you want to extract prediction interval for each level, you can do something like that to extract the lower bound and upper bound of each level. I think we almost there. Let me just very briefly talk about this fitted value and residual, but I will come back to this in day 5 as well. So when we train a model on the data, so using the model function, what actually model does is goes and creates what we call the fitted values. So these fitted values are one step ahead forecast. So it is like, we have a sort of equation. We go to the beginning of the time series, and then we forecast from the first observation, depending on the equation, for the next one. And then we go to the next period. We produce the forecast for the next one based on the observation we have up to that point. So in each step, we produce a forecast for the next step. This is what we call fitted values. Well, we have also residuals. The residuals are the difference between fitted values and then actuals. And you can extract them using a function called augment. So again, this is our model table or Mabel. So I could pass it using pipe operator to augment as well. And if you do that, then you get those information we had before. And actually, in this case, this is the point forecast, the actual. Sorry, this is not the forecast, it's just the actual. And then here we have dot fitted, which corresponds to the fitted values. And then dot resid, which is the residual, the difference between this and that. Here you have some NAs. This is because we use seasonal naive in this case. And then because it's a quarterly data, the first estimation that we get is from 4 periods before that. So if I want to get estimation from this period, right here, I need to go back 4 periods to be able to do that, right? 1, 2, 3, and 4. And that's the first estimate that I can get, but I cannot get anything for them because there is no other observation before. So augment helps you to extract this. And then if you want, you can go and visualize the fitted values against the actuals, or even you can plot the residuals. And these are like some really helpful information that we use later in day 5 to see how residuals could help us to understand whether the model that we apply to the data captured the systematic pattern available in the data or not. So residuals are important to help us evaluate the performance. Okay. Let's see, I think there is a question. Can you use ggplot instead of autoplot to plot the model? Yes, actually, for one of the things that I used here, I use ggplot. So you can always use ggplot. So here, I use ggplot to create that, and so you can do that as well. So, well, again, the recommendation of, so there is a question about, is it recommended to use naive and seasonal naive forecasting for longer horizons? Well, it depends on the data, really. So, you cannot, just by not seeing the data, you cannot say that which method is working for which data. So different methods may work for different data. So depending on the time series that you're working with, well, possibly naive could be the one that you use. And if you have like a strong seasonality in the data that repeats, and it wouldn't, of course, with the assumption that that wouldn't change in the future, probably seasonal life would be a reasonable choice, even for long term. But again, it depends on what you mean by longer horizons. So sometimes they could, but as I said, I don't say that these are the methods you have to use in practice. What I'm saying, these are benchmarks. And I explained why we have to include benchmarks in the modeling. How would you forecast the yearly number of admissions in emergency ward? Oh, I'm not sure what you mean by yearly number of admissions in emergency ward, and how actually forecasting yearly is helpful in admissions. I suppose maybe, do you mean maybe a daily forecast over a year, or? Because I can't see how yearly forecast is very helpful in emergency department. So if you want to forecast, let's say, hourly and daily in emergency department, so emergency data, they have very often multiple seasonality. So they have within day and within week, and actually within year as well. So you need approaches that take care of those kind of patterns. That's one important thing. Emergency departments are often affected by many types of events, so you need to capture that as well. And then you need also to capture the interactions between different things that happen. For instance, in an emergency department, the hour of day and the day of week interact. So for instance, if you work on Friday and Saturday in emergency department, you will get more patients, let's say from midnight to 3, 4 a.m. So that interaction sort of thing are important. So they require like considering all this information and building models. So the benchmark method that we introduce here, they don't take any predictor. But if you work in an organization and you have a simple regression model, you can always add predictors to the regression model if this is what you have as a benchmark to improve. But the one that we have here, they don't have predictors. So Mitch, we talk about regression this afternoon, and the regression model is the one that you can use to add predictors. Yeah, so this is a good question. How do you settle on an interval for converting the forecast distribution using the halo function? What determines which interval to be best one? That's a good question. The answer actually depends on the context that you're working on. So, for instance, if you work in, let's say, a supply chain, and you need to have, let's say, replenishment policies, in general, you have to satisfy a certain number of demands that comes to your service or organization. So if that is the case, so you have a service level. So the service level maybe is about 90%. So you say, I have to deal with any demand that comes to my service 90% of the time, okay? So if you are happy 10% of the time, let's say, if there is a demand and you cannot satisfy that, you say that, well, I take that risk. But you want to satisfy 90%. So if you do that, 90% one, it means that the prediction interval that you are actually going to cover, it is going to be, because that 90% often is about a quantile, right? So that 90% determines what prediction interval you're going to use there. And if it's 90% quantiles, then there is a sort of relationship between a quantile and a prediction interval. Okay, so it depends. It's a good question, but it depends on the context. It depends what you are going to actually how your forecast is going to inform the decision. So there is no default really. It depends on the context. But here the idea is to extract any interval that you want using the level. But in many cases where you are dealing with demand, so the interval could be something around 90%. But again, it is about the service level that you set in your organization. So 90%, I think, is something people use often. Okay. Something, it seems like someone is on road and listening to us. Okay, I think we can have a break. I think maybe 10 minutes. There is one more question that I can answer after the break. And then I think Mitch will take over the next one. Okay, so let me pause here. Yeah, so there is one question about when we are using daily data, and there are some days where there is no sale. Basically, actually there is a function in Tessable called fill gaps. Sometimes, depending on how you receive the data, there are probably some period of time where there is no recording for that period. So here, if you have transaction data of the sale and there is no data for certain days, or if you work in a hospital, there is no data for certain hours, these are some temporal gaps, and we have to deal with temporal gaps before proceeding with the time series analysis and forecasting. So in this case, if you are sure that actually those periods are corresponding to no sale, well, I will just replace them with 0, really. And if you have zeros in a time series, we call them intermittent time series. And they are a special type of time series. They require different ways or different approaches for forecasting. And actually exponential smoothing that we cover tomorrow could be a way to deal with also time series data with 0 sales. So that's one thing. Another thing is, of course, sorry. So another thing is, yeah, there might be those periods might be also, I don't know, affected by certain events. So you may also go and collect information about the events and include it in the model. But yes, you can forecast them, and they will affect the models. But there are certain models designed for this type of time series that can be used. And again, the term here is intermittent time series, which is more relevant to this discussion. All right, I think Mitch, so we can start maybe now.
Okay, thank you, Bahman. So let's take that again with the recording on this time. So welcome back from the break. I hope you had a nice little stretch and got some water or whatever you need. And we're going to continue on with a more advanced model. It's a model that you probably have heard of before if you've done some statistics. It is the regression model, simple linear regression, or multiple linear regression in many cases. The time series version that we're going to look at now is quite similar, and in the structure, it's the same as what you've already seen for cross-sectional. However, we use some special regressors that are designed to capture the trend and the seasonality. And we're going to focus on that today because it helps you think about those terms in modeling, which is useful for tomorrow's more complicated models. So for the website, Bahman's introduced the basics of modeling, in particular some time series benchmark models, which are very simplistic. And now we're going to use a very general form of a model for time series forecasting, which can still include trend and seasonality, but in addition to what was possible with the previous models, a regression model can do both trend and seasonality at the same time. And it can also, of course, incorporate other information from other variables. So this is a powerful tool for forecasting if you have extra lead time information. So if you click through there, you'll find the materials that I'm about to share, the slides. And this is all about forecasting with regression. How do we represent temporal structures like trend and seasonality using regressors? So if you haven't heard of the linear model before, this will be a nice primer for you. Regression models are twofold. They help explain the relationships between your response variable, the thing that you're trying to forecast, and the predictors. Those predictors might be trend and seasonality, but they could also be other things like temperature and GDP, for instance. They can also be used to make some predictions. So for the time series domain, we often use a regression model in order to forecast the future. And you may have heard of simple linear regression or multiple linear regression. They're all the same thing. Simple linear regression just has one regressor. Now, if you've seen regression before, this might look familiar to you. This is a simple linear regression model. On the left side of the equation, we have our response variable, what we're wanting to forecast. And on the right, we have what we're using to forecast it, plus our error term that Bahman was talking about before. In this case, we're using an intercept plus a regressor. A numerical variable x1 or xt is what we're using to predict the changes in the data, yt. So this is a linear regression model because we have a combination of regressors that are additively combined with some scalar coefficients, our regression coefficients. Now, usually we don't know what those coefficients are, so when we make a prediction, we estimate those coefficients in order to make a prediction of yt. And I would also like to see a little yt hat here for when we're making a prediction because we don't know what the error is. Visually, it looks a bit more like this. You might have a cloud of points, these dots, and we fit a line through the middle of them in a way that minimizes the optimization criterion. And usually we want to minimize the errors. So we measure the errors vertically from their location to the position on the line. And we've chosen this diagonal red line in order to reduce the errors as much as possible. In fact, when we reduce the errors, what we're trying to minimize is not the total error, but the squared error. Other versions of this, which is not least squares, you might consider doing the least error, which you might use the absolute error for instead. But for all of the regression modeling we're using today, and with time series, we'll be using squared error. The equivalent way of representing this is to use yi minus our prediction of yi. And I would again put hats on beta 0 and beta 1 here because we're using estimates of those coefficients. So note the distinction between estimated coefficients and underlying coefficients. We put hats on whenever we're making a prediction or an estimation. So here's an example of a time series. We've seen this time series before, but we've not looked at these variables yet. Here we're looking at US change for consumption and income. Let's switch back to R. We'll switch over to R. As usual, we'll load in the FPP3 package to get started. This loads all of the data sets and tools that we need to run the code and produce the plot. And we're interested in the US change dataset. So previously, we looked at this dataset for unemployment, but there's a few other variables here that are interesting to us. So let's suppose we're interested in forecasting the consumption. So I might auto plot consumption to produce our time plot. And looking at this, there's not much structure. We don't see much trend. There's not much seasonality, but maybe there's some other information in this data set that we can use to model what the consumption might be. So looking at some other variables, maybe we consider income, the next column. And this also doesn't have trend or seasonality, but it has a few increases that might line up well with this one here. But flipping between both plots isn't very helpful. It's hard to compare them. So what would be nicer is if we could add on both lines at the same time. So I'm going to add another line for my income data, and I'm going to make the color of this blue. Sorry, I've plotted income on top of income here. Let me fix the underlying plot. So I'm trying to predict consumption, and I'm going to compare the consumption data, which is shown by this first auto plot, with the income variable by adding a line of income on top of it. And following this, you can see there's quite a lot of similarity between the two variables. When the black line is higher, that's consumption increases. We see that income increases as well. And then when it drops afterwards, income follows it too. So we might like to model these two variables together with a regression. Yes. So I've shown you both of these variables in time, but when we're thinking about regression, especially with multiple variables, we often like to model it in terms of a scatter plot. Compare the response variable on the left side, the y-axis, the consumption, with the variable we're using to predict income on the x-axis. So let's see how to make that plot. Now there's no auto plot to do this, but we can use ggplot directly. I will put on the y-axis consumption, and then on the x-axis I'll put income, plus g on point for a scatter plot. So it doesn't seem to be that much similarity in a scatter plot, but if I draw a line through this, at least squares fit, using geom smooth, and say the method is a linear model, you can see that there is some positive relationship between them. So it is reasonable to estimate a regression model between these two variables. Now, just like Bahman showed for the benchmark models, and we saw yesterday for the STL decomposition model, we can estimate a model for regression with the same model function. And the function for regression is TSLM, time series linear model. And just like we use the formula for STL decomposition and benchmarks, we use the formula for regression too. And this looks and behaves very similarly to what we use in base R for the LM. So here I'll put consumption on the left side of this tilde, and I'm going to use income to make a prediction about consumption. When I run this code, I get a Mabel once more, and I've got my single model here in the dataset. Saving this as fit because we'll use this later to produce a forecast. Now, once we have our forecast, there's various things that we can do with this. Just like we saw with the benchmark models from Bahman, we can use the tidy function to extract the coefficients. We can use the glance function to get a summary of the results, and the augment function to get our fitted values and our residuals. You can also use the report function, which behaves very similarly to the summary function and gives you a nicely formatted output to tell you about the coefficients of the model, the structure of the residuals, and the significance of any terms. So let's try those model functions. So I can tidy the model to get the coefficients. I can obtain a summary using glance. And I can get my estimates, or my fits, using augment. And lastly, I can get a summary, a report, using the report function. So let's look at each of these. If I use the tidy function, you'll see I get a tibble back. And this is really useful for if you've got many models and you want to compare the coefficients across multiple different time series. Let me get some more space for this output. You can see the first row, we have the intercept that has the estimate of 0.545. So when income is equal to 0, the line here is equal to 0.545, and that seems correct. Sorry, I'm blocking that. Make it a bit bigger. So when the income is 0, the line here matches the intercept coefficient, 0.545. Now the slope, you can see that it's increasing, but at what rate? For this, we can look at the coefficient of income, and we can see 0.272. So before, when we looked at the slides, and we saw that regression models are useful for explaining the relationship between regressors, this is what we mean. We can look at the coefficients and make interpretations about the relationships between our response variable and our regressors. So what this 0.272 means is when income increases by 1, on average, we expect the consumption to increase by 0.272. What about glance? Glance gives you some useful statistics like the R-squared, which is used to explain the variance explained for the consumption based on variance of the regressor's income. It also shows you the sigma squared of the residuals, the variance, along with the overall significance of the model. Now, what's particularly interesting here is our information criterions and our cross-validation statistic. This is useful for us to compare multiple models. So perhaps I had 2 models here. Maybe I wanted to see consumption against an intercept and consumption against income. So now my model contains 2 different regression models, which has in the tidy output 2 different intercepts. You can see the intercept for the first model was 0.742, but after including income as a regressor, it decreases a bit, so we can compare models with this. If we look at the glance output, looking at the cross-validation statistic, we can see that the second model is better. It has a lower cross-validation statistic, meaning that the second model, which includes income, is better. So we don't want to include this model that just has an intercept. So glance is a useful summary of the performance of a model. Augment gives us our fitted values, our residuals, and our innovation residuals. Now there's a slight difference between residuals and innovation residuals. When you're testing the model, which we'll do in week 5, we often want innovation residuals for diagnostics. But if you want to see how well the model's performing, you want these residuals. But here we have the actual consumption and the fitted values, which we saw earlier, we can use to make a plot. So if I auto plot consumption and add a line of my fitted values on top, we can get an idea for how well our model performs. So the black line is the actual data, and the blue lines are what our model makes as predictions. Lastly, from the report output, we can see the coefficients again, but it's organized in a slightly nicer table for us to read, and we get our p-values for the significance of these regresses. So more often than what I've just shown you, we'll actually use several regresses in the same model. And this is known as multiple linear regression, and it behaves very similarly to what we've just seen. However, there's a problem. If we add lots and lots of regresses, we can start overfitting, and our regresses might suffer from multicollinearity. So we need to choose a specific number of variables that are relevant to the forecasting problem. Often in regression models for time series, this isn't such an issue because all of the regression terms, like income that we just used, need to be forecasted. So we have some motivation not to include too many variables. Otherwise, the model becomes complicated to use for forecasting. But multiple linear regression, you can see rather than just having beta 1 xt, we now have x1t, x2t, and all the way up to xkt. So we've got several regresses that we're using together to predict yt. So now the coefficients, beta 1, beta 2, beta 3, and so on, are measuring the marginal effects. What that means is the relationship between x1 and yt after taking into account the relationship between x2, x3, and xk, all of the other predictors in the model. Just like before, we need to estimate these coefficients, and we do that by minimizing the sum of the squared errors, or equivalently, yi minus the prediction of yi. So linear regression is often known as least squares modeling because of this optimization technique. And once we optimize the coefficients to minimize the error, again, we put the hats on the coefficients to indicate that they are estimated coefficients, not the actual underlying relationship. Now, in a time series context, what makes time series linear modeling a bit more special is the special functions for representing linear trend and seasonality. So a linear trend is quite simple to incorporate into a model. We just need a straight line that goes upwards. And then the strength of this line, for if it's going to be a very steep positive trend, a less steep positive trend, or even a negative trend, we use the beta coefficient multiplied by this increasing number, which is just time, 1 up to t. Capital T is the end of the time series. And to incorporate this in the model, just like before when we used the trend window and the season window for STL decomposition, we can use the special functions trend and season to include a trend and a dummy variable seasonality. So in this particular time series that we were looking at, we didn't notice much trend or seasonality in consumption, and there wasn't much of that in the other variables either. So we'll come back to this for modeling more, but first I want to show you the linear trend and seasonal terms. Okay, so let's pick out a data set from yesterday, which worked quite well for us. I think the tourism, let's not do tourism, let's do US employment. Retail trade. I think that was pretty good, pretty interesting. So as before, all of the code and data has been provided to you. The code that I showed you yesterday in day 2, I've put up on the website, and I'll be putting up the recording of day 2 shortly. So if you remember this data set from yesterday, we saw that we had seasonality that was additive for this section of the data, and it's got an upward trend. So let's try to model this using a linear regression model. But first, I'm going to save the data set that we've filtered out to be isolating this one data set before plotting it. And then I can use TSLM of my response variable, which is employed. And I'm going to start with just an intercept. So again, we get my regression coefficient here. Now, I don't think this model will do very well because it cannot capture the trend and seasonality that we see in the data. But let's see how it did if I augment the data and then use the same code as above, where I auto plot my response variable and then add on my fitted values. You can see just using an intercept doesn't do very well. It's just a flat line through the center of the data, and this corresponds to the average, and this should give you the same results as the mean method that Bahman introduced in the previous session. So instead of having a constant color, I'm going to color it by model now. Model is a identifier for the model used. So rather than coloring it by that, I'll color it automatically by model because I want to compare multiple models here. What if I use a trend? So we saw the trend special before in the slides. If I use trend on the right-hand side, it will automatically create the regression term needed for a linear trend. So I'll do my intercept plus a trend. And now when I plot them, the color will match the model that I specify. So I've got two models here, and accordingly, I get two lines. I don't quite like how the colors are working for the base time series. So I'm going to change this a little bit. Rather than using the augmented results for the plot, the base plot, I'm just going to use my original data. So now I get my black line being the data. But if I try to run this, I don't have my model column or my fitted anymore. So I'm going to use my augmented results only for that line, for the colored line. So you can add data to a specific layer using data equals your data set. So now my original data plot is shown as before, and I'm adding on lines for my fitted values. And you can see hopefully the red line, which is my new model that incorporates trend, does a better job. It's following the upward trend that I have in the data. It's not perfect because the trend isn't linear. We've got some sharp parts, some flat parts, decreasing and increasing, the cycles that we were talking about yesterday, and this trend term won't capture that. I can also use the season term to incorporate the additive seasonality that we see in the data. So if instead of trend, I use season, what we'll end up with is dummy variables for each of the months, and that will estimate the seasonality. But this also isn't very good because I don't have the trend. However, with regression modeling, we can include both. So we can include both a trend and a seasonal term in order to get a reasonable model for this data set. So this new green line, I'm going to remove the other ones now. This red line captures both the size of the seasonality and the linear trend. It's not perfect because it doesn't follow the changes in the trend, but there are some improvements that we can add to follow this shape, and we'll talk about that in a bit. So a linear trend has a very strong assumption that the trend continues in a linear fashion. And what we've just seen when the linear trend doesn't continue is that it doesn't work that well. And same for the seasonality, we're assuming that the seasonality is constant and doesn't change over time. Okay. So now what I'll show you is how we improve upon this trend if it's not completely linear. What we can do is introduce knots. And what a knot is a breakpoint in the trend where the trend is allowed to change. So you can see in the year 2000, the trend was going up beforehand and then is pretty flat afterwards. So we can improve the trend in our model by setting knots. The knot will be at 2000 January. Remember the year month function that we use to convert a date or some text into a time point? So I'm going to use 2000 January, this point right here, as a change point for my trend. So inside the trend function, I say knots is equal to year month of that point in time. And what you can see now, let me give this a name. When we introduce knots into that trend, we call it a piecewise trend because it's pieces of linear trends. And we'll compare this with linear. If I add names to this, I won't get such long labels. Okay, the blue line is the new model with the piecewise trend, and it's looking much better. You can see the first section of the data is much closer to the actual data, but we still have some issues towards the end because we've got this big drop at 2010 January that we'd like a different estimate of our trend for. So I can add multiple knots here with a vector. Let's also add a split at 2010 January and add another bracket to close it out. So adding two knots, you can see I've got three different trends now: before the first knot, between the first and second knot, and then after the third knot. After the second knot is my third trend. And you can add lots of these little knots in order to follow the data for the trend. But if you have a trend that changes as much as this one does, it's probably better to use a different model like ETS, exponential smoothing, or REMA, which we'll see tomorrow. Just for the code there, I've used on the left-hand side my employed variable, what I'm trying to predict, with an intercept, a trend with two breakpoints, knots at 2000 January and 2010 January, and then adding on some dummy variable seasonality. Okay, let's go back to the US consumption example. Often it can be a bit tricky to choose which variables to include in your model. And for this, it's useful to use plots to see the relationships between these regressors. If I plot all of the variables, consumption, income, production, savings, and unemployment, you can see income follows the patterns the closest. And that is why we used income in our model. You can also see some relationships between production and unemployment, for instance. When there's a drop in production, there's an increase in unemployment, and that should be fairly intuitive. A useful plot to compare all of the regressors at once is this scatter plot G-Gally plot, GG pairs plot. And what this does is shows you the density of the distribution of the variables in the diagonal, the scatter plot between them. So consumption and income is what we used before. And you can see that there's a positive correlation there. And in the opposite diagonal, we can see the correlation was 0.4 between income and consumption. This helps us see stronger correlations, like between income and savings. You see there's a stronger relationship between the two here. And this corresponds to, let's find it. It was income and savings, 0.714 is our correlation. So that's much larger. Similarly, we talked about the relationship between production and unemployment. They're kind of inversely related. And you can see that negative correlation here between production and unemployment. And the negative correlation is roughly negative 0.8. So very strong negative correlation. Now, with multiple linear regression, you can of course put all of the terms in your model. So we just had income before, but just like we had trend plus season, you can do income plus production plus unemployment plus savings, and then see which of the terms are significant. And from this, we can see income, which we originally chose to include in the model, is significant and worth including. And savings is also related to the consumption. But it has a negative correlation, negative relationship with consumption. And when we include all of those terms in our model, you can see we get a much closer relationship between our predicted values in blue and the underlying data in orange. And here you can see the relationship between the actual and the predicted, and we get a quite strong relationship, a very accurate model. I'm going to skip this. I'm going to leave this for day 5, but this is a useful way that we can see how well the model is performing. And we're going to look at this in the final session for residual diagnostics. Okay, so we have a few assumptions that we'll be checking in day 5, and these relate to the correlation. If you remember from when we looked at the ACF plot in day 1, the correlation is shown in the ACF. And if you look at this ACF, we don't see any patterns, and that's what we hope to see, because we hope that our error term, whatever's left over from the model, has captured all of the information available. It's also nice to have the error being normally distributed. We can see that from the histogram here, which looks pretty normal. And this is useful for our forecast distribution. We assume a normal distribution when we make our forecasts, and if we don't have that, we have bad prediction intervals. So residual diagnostics we'll revisit on day 5, but it involves looking at each of the plots here in order to see how well our assumptions line up. Okay, we don't need to look at residual diagnostics. So for selecting predictors, we estimated a regression model that included all of the variables that we had. That's this one here, but we saw that production and unemployment weren't significantly related. So do we need them in our model? To do this, we can use some summaries of R-squared. And there's a problem with R-squared in that it will always increase as we add extra variables. However, we can incorporate the degrees of freedom, which is related to the amount of regressors we have in our model, to produce an adjusted R-squared. And if we go back to R, for my employment model, my consumption model, if I include all of the regressors, which I can do with the dot, and glance the results, and in fact I'll tidy the results. I'm modeling consumption with consumption. I can't do the dot. I could minus consumption, like dot minus consumption. So that means all variables except consumption. And probably except time as well. At this point, I will just put all of the variables in. Income plus production plus savings plus unemployment. Okay, so I get my set of coefficients from this with their p-values. Some of them are very significant, others aren't as significant. But is it an improvement on the model? And for this, we can look at R-squared, but that doesn't incorporate the degrees of freedom for all of these extra variables that I've included. you can see that R squared is much higher, but the adjusted R squared in the next column over is more interesting to us. And you can see by including these extra variables, we've got an R squared and an adjusted R squared that is much higher and therefore better than our model that just included income. But what about if I just had, maybe I remove production? I don't think production is so important. And you can see that the R squared is of course lower because we've removed a term from our model. And the adjusted R squared is also slightly lower, but not nearly as much as the actual R squared. So that would be an argument for including both terms. Maybe I remove savings. When I've removed savings, you can see that it's had a huge drop in the model. So we definitely need to include savings. And if I remove unemployment, you can see that there's a slight drop here. So if I wanted a simple model, I could probably just use income and savings and still get quite a good R squared or adjusted R squared. But the adjusted R squared, considering the degrees of freedom lost, would suggest that we'd prefer the full model. So often we like to maximize the adjusted R squared, which is a useful way to avoid overfitting. Because if we keep adding regressors, the R squared will always go up, but the adjusted R squared will take this into account. However, a better statistic for this is the CV statistic, cross-validation, and we talked about this just before. And this is also provided in the glance output. So we want to minimize the cross-validation statistic, and you see that's also done when we include all of the terms in our model for this example. And you can see including income alone doesn't give you a very good model. But there's also the more practical consideration of how easy it is to predict production and unemployment. Maybe it's possible to predict income and savings so that you can produce a forecast for consumption, but this requires some extra work. So you can get most of the performance with half of the regressors by removing production and unemployment. So this glance output provides a nice summary of what's important. You can also use Akaiki's information criterion. The cross-validation statistic here is better for regression models, but when we look at ETS models and ARIMA models tomorrow, we'll be using AIC quite a lot. But just like the one before, it penalizes for each additional regressor you have. We've got this plus 2k, k being the number of parameters in the model. So we want to keep the AIC small by reducing the number of parameters in our model while still getting a good estimate. There are some biases here, so more often than not, we'll use a corrected version of that. The specifics aren't so important. You can see it's slightly more complicated for the number of parameters. But the same as the AIC, we try to minimize the corrected AICC. So we saw from the glance output, we have all the relevant statistics that we need, and we can find the best possible model by removing some of those regressors in order to optimize the best statistic, CV, AIC, or AICC. So you can start with a model with all of the regressors and just remove one variable at a time to see if it produces a better CV or AICC. And when you finish that, when you can't remove any more variables without worsening the model, you've got a simple but good model. Okay, let's think more about forecasting. I think this is what I want to talk about most here. Forecasting with regression is perhaps more difficult than the benchmark forecasts. And that's because we require to produce forecasts of our predictor variables as well. So depending on our choices of what to include in our model, if we're including unemployment, savings, and the other variables here, in order to produce future values or predict future values of consumption, we need to also produce future values of the regressors, and that can be quite difficult. Now, some of these variables, the time-dependent variables like trend and seasonality, these are very easy to predict because we know what the time points are that we're forecasting. And so when we use the trend special and the season special, we don't need to provide the future values. That will be calculated for us automatically. Now, even if we don't know what will happen next for our regressor models, doesn't mean the model isn't useful. Remember, regression models are good at explaining what happens. And one useful explanation for future values is to do scenarios. Maybe we can't predict the future income rate for the US or the savings rate, but we can make some educated guesses or set up some scenarios that can be useful for policy making. Maybe we want to decrease consumption, and to do that, we might like to produce a scenario for if we can reduce savings by 10%. So when we use the future values, set up the future values for our forecasts, we need to provide the future values of our predictor variables as well. And depending on if we know the predictors, we can put in the actual values, but more often than not, we don't know them, and we can put either what we think it will be using a forecast or an expert opinion, or we can use a scenario forecast to say, what if the future savings was 10? Now, if you're only interested in producing short-term forecasts, it might be more easy or more reasonable to use lagged predictors instead. That way, when you forecast one step ahead, you can just use the current value, the most recent values, as known future values. Let me show you what I mean by that. So let's say we've picked our favorite model, which was consumption against income and savings. I'm going to bring this right to the end. So my favorite model was consumption using income and savings. And just like you saw in the previous session, I'm going to forecast maybe 1 year ahead. But I encounter an error here, and you probably won't get this browser, but you'll get this message in the console saying, income not found. I was unable to compute the required variables from the dataset provided. Do you need to provide some extra information when producing the forecasts? And this can be quite difficult because unlike the previous model, US retail, when I only had trend and season, here when I produce forecasts 1 year ahead, let me run that again. Oh, not US retail, FIT, sorry. With the historical data. Here I'm using the same regression model, but my regressors are just trend and seasonality. So these can be generated into the future as well, giving me my forecasts. However, because my other model here requires income and savings, there's no way to automatically calculate what they are. So I need to calculate or provide future values of that, which is tricky. And I'll show you how to do that. But first, an easy fix is to use lags of these regressors. So rather than using the matching time period, I use the day before, or in this case, the month before, which will allow me to produce a model using lags of those relationships. You can see the relationship isn't as strong anymore. But because I'm using lags, I know what happens next, just 1 day ahead or 1 month ahead. So when I produce forecasts, oops, I do need to set this up actually. In future versions of the software, this will be a bit easier. You can blame me for not having that working here. Okay, so when you get this error with regression models saying income not found, please provide new data, you'll need to say what the values of income and savings were for the next value. So we can do a scenario for what if income was 3 and savings was 1. That's what's happening next. I'm going to save this as future US change, which is a symbol with 1 observation. So now when I come to forecasting, I'll rearrange this a little bit. Rather than using h equals 1 year, we specify the future values. Future US change is my new data. Like so. So because I'm forecasting 1 step ahead, I'm providing 1 future value for income and savings. And from this, I can get my forecast, and it will only be as good as the data that I provided it. The income equals 3 and savings equals 1 is a huge assumption to make. And you can see because I've produced bad values for that, my forecast is pretty terrible. But if I produced more reasonable values, maybe the average of the data, and the mean of US change dollar savings. If I use the average of these regressors, which is a simple way to forecast it, you can see I get a much more reasonable value. But I might do a scenario. What if the savings was the average plus 0.3? What if we could increase it by a little bit? How does that change the forecasts? You can see it didn't have much of an effect. It decreased it by just a slight amount. But what if the income was to increase by 1? If everyone's income increased by 1, then the consumption will increase substantially. So perhaps more realistic is to use lags, because then we reserve some information for our future values. So when I come to forecasting with the lag, I will instead use the most recent value of income and savings for my 1 step ahead forecast. So now I don't need to provide what the next value of income and savings is. Because instead I will be able to use, oops, I need to rerun this model. I guess I need to put something in here. Okay, maybe this lag isn't working. There could be a bug in the version of the software that I'm using. I'm not sure if this will work for you, but I'll get this fixed. This should be possible to work with. But regardless, I will explain the lags. The advantage of having predictors being in the past is that you know what will happen the next month or 2 ahead. And so when you forecast, you shouldn't need to provide those next few values. It should be able to use it from the existing data set. Sorry about that. I guess I've got my work to do, improving the software. So here we show the scenarios that I was talking about. What if income was to decrease by a little bit, savings were decreasing as well? Or what if they increase? We can create multiple scenarios based on what might happen next and then compare them. So the increasing scenario gives us this forecast. But if everything were to decrease, the consumption will drop substantially. A very common confusion with regression models is with the explanations. So when I talked about the coefficient and interpreted the increase in consumption based on income, there's a bit of a catch there in that it's not necessarily a causal relationship. It's not because income increased by 1 unit that consumption increased by 0.272. Instead, this was just the correlation between the two variables, the relationship that we could see in the data that we had. And there's a nice website here called Spurious Correlations, and this puts two completely random topics, two completely random time series together that happen to have a very high correlation. So in this case, the example is that drownings in pools happens to correlate with the Nicolas Cage films of that same year. So in 2007, you saw the same big drop, but in 2008, they both dropped as well. Does this mean that the films that Nicolas Cage appear in causes people to drown in pools? Of course not. So we need to be very careful when we interpret our model that we're not creating causal relationships here. We're not interpreting them as causal relationships. They just happen to line up. So in this case, X is useful for predicting Y. In other words, savings was useful to predict consumption, but it doesn't necessarily cause the changes in consumption. And just because we don't have causality, which is much harder to show, doesn't mean correlations aren't useful. We can use these correlations to produce good forecasts. However, if it is possible to produce a causal relationship, this would be much better. Now, I talked a little bit about multicollinearity before and overfitting. Multicollinearity is when you have two or more regressors that are very similar. So if their correlation between the two predictor variables is almost 1, or -1 for that matter. Now, if you have these highly correlated predictors in your model, you can cause some estimation problems. And it's encouraged that you remove one of those predictors or more, so that you only have one of these strongly correlated regressors in your model. So we use a subset of the predictors that are highly correlated to produce our model. Now, if we choose to include all of the regressors that might have multicolor linearity, the numerical estimates, the coefficients are probably wrong. So if we're making any interpretations about p-values and significance, they will also be wrong. But the predictions that we make from the model are probably still okay. Usually they work fine, even if we have multicolor linearity. So this isn't a problem for forecasting. The solution to this is either removing the strongly correlated variables or combining them. Now, there's a few things to watch out for regression models, and this is something we'll revisit on day 5 when we look at our residual diagnostics. But we want to be careful with outliers, because outliers will produce large residuals, and large residuals will produce wide intervals. We also need to be careful of very influential observations. If we have outliers, then they might have a large effect on our estimates, because remember, we're minimizing the squared error. And squared errors that are large will become very large, and that will have a big effect on our estimated parameters. Also keep in mind, if you don't include a regressor that is important, then your model won't be as good as it possibly could be, and your interpretations of the coefficients could be inaccurate. They might be representing other regressors rather than the effect of other regressors rather than the effect of itself, like savings. And just a note here, I discourage you from picking and choosing different observations. This isn't really an issue for time series, because you often don't want to remove observations in time. But when you're working with regression models, you should keep all of the observations unless you have a very good explanation for why they need to be removed. For instance, an outlier or a very influential observation. Now, when it comes to selecting a model, it becomes a lot more difficult if we've got lots of regressors, but there are some other types of regression models that we can use to help with this, like lasso, ridge regression, or elastic nets. Now, perhaps the most useful section of this topic for us is the useful predictors specific to time series, and that's what we'll see in the end here. Perhaps we could put in the chat, have you heard of dummy variables in regression before? Or actually better, let's use the reactions. Could you give me a thumbs up reaction if you've heard of dummy variables before for regression?
It is a pool I think you can use as well, Mitch, isn't it?
For Zoom?
Yeah.
Not easily. I think I need to set it up in the web portal. Okay, it looks like a few people have used them before, but not everyone. So a dummy variable... Pardon, Bahman?
I can create, if you want, whenever, let me know, I can create pools in Zoom.
Okay, thank you, I'll let you know. Okay, seems like a lot of you have heard of dummy variables before, but a couple of you haven't. So I won't spend too much time on this because it's more of a statistical issue or topic. But a dummy variable is a way of representing categorical information that has only two values, like true or false, yes or no. And we could use a dummy variable to represent your understanding of dummy variables. If I was trying to predict someone's knowledge in statistics and I asked you the question, have you heard of or used dummy variables before? That would help me model how well you are, how much you know about statistics. So you can see if we have yes in this data set, we have a 1 in our model. But if we have no in our response, we use 0 as our response, as our value. Now, if we think about this with our regression, let me go back to the linear model. We've got yt equals an intercept plus xt times beta 1. Imagine xt now is a dummy variable. So if you said yes to the question, then we would have a value 1 for xt, and we'll end up for our prediction with beta 1 times 1. So we'll end up adding beta 1 to my prediction. But if you didn't know about dummy variables, if your answer was no, then my dummy variable would have the value 0. And so we'll have the prediction being beta 0 plus beta 1 times 0. So this will all be 0. So you can see dummy variables will allow us to add or remove beta 1 from the model, depending on if you do or do not know about dummy variables, or answered yes or no to the question. Now, this is particularly useful for time series for different sections of the data. If you remember the ANSET dataset, let's plot that one. Let's auto plot passengers. So here's the total number of passengers flying on ANSET. We can use a dummy variable to capture the effect of the strike. So if I did a simple model for this, I might have a trend. There doesn't appear to be much seasonality here. So maybe I have a trend, passengers modeled with trend. Save this as fit. And just like I did before, I'm going to add the line of my fitted values on top, augment of fit. I need to set aesthetics, sorry. I make some mistakes sometimes. So put fitted on the y-axis as well. Here's my straight line trend through this data set. Now it's not great. We can of course add in a knot like we talked about before, maybe at 1990. And now we get two trends, which is a much better estimate of the pattern. But we have this big drop in the data for when we had the strike. So what I could do is find out when this strike was. So I'll filter index. And maybe I'll do 1989 until 1990. I need to add a week 1 here. Oh, I've done the same thing I did last time. I need the formula outside of the quotes. So we can see this, the strike seems to be after week 26, and we can narrow in on exactly when this was. Date breaks equals week. That might be too many. So there's all sorts of different functions that you can play around with here. And there's a lot of searching that you can do after this course online to figure out how to produce plots with different different breaks. But with this, we can see that in week 34 until week 40, we had a strike, and it recovered pretty slowly after that. But what we can do is say mutate a strike if we had time in, if our week was between these dates. So it was 34 until 40. And I'll just print lots of rows here so we can see all of the data. And what I hope we'll see is that we've got a new variable called strike. And most of the time, the airline isn't striking, so we have false. However, during this time period that I've isolated, which is from 1989, week 34, you can see the number of flights, number of passengers was 0. And I've programmed it to say there was a strike. Strike was equal to true. Now, a simpler way to do this would be saying passengers equals to 0, because it was exactly equal to 0, and that will give us the same result. So we've found when the strike was, and with a dummy variable in our model, I can now add on strike as an extra regressor. And you can see the effect of that dummy variable has led to a huge drop in the predicted number of passengers. So we've got a much more accurate forecast now. You can even do interactions between these regressors, which would be even better. So now I have a flat line for the strike here. And my trend won't be affected, this downward trend won't be affected by the few days of strikes that we had. So dummy variables are useful for incorporating short-term events that might have happened. Maybe the pandemic has impacted your dataset in some way. You can add a dummy variable to have a different predicted value during the time of pandemics. And then if a pandemic might happen in the future, suppose you're saying there's a scenario, you can say true, yes, a pandemic is happening 3 years from now, and see how that affects your forecasts. Now, where this is particularly useful for us in time series forecasting is with our seasonality. And I previewed the seasonality before, but if I have days of weeks, Monday, Tuesday, Wednesday, Thursday, Friday, only the weekdays, I can use dummy variables to represent what day it is. If the first row was equal to Monday, then I would have, if the first day was a Monday, then I would have 1. And because it is a Monday, then the next day wouldn't be. It would be a Tuesday. The day after that's a Wednesday. So for day 1, we can see that it is a Monday, but it's not a Tuesday, Wednesday, Thursday, Friday, and so on. And this is quite easy to do in R. We saw how to do it already. You can just add directly the season function, like so. Now, there's a little bit of an issue here with the interaction between dummy variables and the intercept. If you include all of the dummy variables, then you have multicollinearity again. You can add up all of those dummies and you'll always end up with 1, and that 1 value will be exactly equal to the intercept. The intercept is just a column of 1s as well. So to fix this, we can either remove the intercept or remove one of the dummy variables. And then that removed dummy variable will become the base category that is that the other dummies that are kept in are compared against. Now this is important when we consider the coefficients of the model. Okay, we had this model here before. Just to remind you of what this model was, we had a trend and a seasonality, and we added some knots. If I tidy this result, for the seasonality, you'll see that it starts at season year 2. This means because we've got monthly data, this is February. We don't have January in this set of dummy variables. And so this negative 200 is saying we will have employment 200 less than the base category, which is what's not shown. So we'll have 200 less than in January. And then for March, we'll have 182 less than January. Whereas in August, the 8th, we'll have 60 more than January. It's always comparing to the dummy variable category that was removed. So here's how it relates to seasonal dummies. To avoid the dummy variable trap, we always use one less parameter than the number of observations in the seasonality. So as 4 quarters in a year, we'll use 3 dummy variables. 12 months, 11 dummy variables. 7 days in a week, we'll use 6 dummy variables. So we saw before for outliers, I talked about the strike for the Ansett flights. That would be an outlier, and we could remove its effect by including a dummy variable. And we can also use this to represent public holidays. And this is shown in the Victorian electricity dataset, where we have a dummy variable here saying if that day was a holiday. So for the first of the year, we have New Year's Day, and that's a holiday. But if I print a few more rows, You can see on the second day, it's also a public holiday in Victoria, but on the third day of the year, we have false, saying, no, this isn't a public holiday. So you often might have some interventions like spikes and level changes or changes in slopes. There's lots of different ways that you can use a dummy variable. If you've got a spike, you might just want a dummy variable at that one point in time to remove it. If you've got a step, like an intervention, you might want that dummy variable to be false for most of the time series and then true for the rest of the time series. And what that will do is your time series might be fairly flat, but as soon as it hits the dummy variable, it will take on that coefficient. So it might jump up a step and then continue flat from there. The other thing that we've seen is the change of slope. So another way, unlike knots, is to handle a change of slope is that you can include a dummy variable interacting with the trend. And I show you that just before, where we had the trend multiplied by the strike. This will also produce a different slope during the strike and outside of the strike. And I used that in order to produce a completely flat set of fitted values here. I wanted a different trend that wasn't negative. So I used the interaction. So here's some examples of holidays that you might use with a dummy variable. If it's Christmas Eve, then set the value of the holiday to be 1, otherwise use 0. You can also do this for New Year's Day, Ramadan, Chinese New Year, all sorts of different holidays with dummy variables. And I showed you how you can interact two regresses together using this asterisk. This is particularly useful for dummy variables. I'm not sure what's happened to this equation here, but the lagged predictors that we talked about before can also be used with dummy variables, and they're useful to include in your model. This is a directional thing. It's saying that the values from the past are used to predict the future. And you can use different lags as well. You can start at the current time, lagged 1 time, lagged 2 times, and as far back as you need, as far back as relevant to include. So we saw how to produce lags in R using the lag function, and you can do this on any of the regresses that you have. So if you want strike, we can also say plus if there was going to be a strike, if there was a strike yesterday, what effect that has on my model. So here's another time series that we might like to look at, insurance. And let's see this in R together. It'll be the last example that we look at. Insurance has 2 variables. It has the quotes, the amount of sales that they're making, and their advertising, how much they're spending promoting their service. So if we auto plot quotes, what we're interested in forecasting, you can see there's not much pattern here. So this is a good application for a regression, because hopefully we'll get more information based on the advertising. So if I add in a line for the advertising with a nice color, you can see there's a very strong relationship between these 2 variables. If they increase the number of TV advertisements, the number of quotes that they get seems to be directly related to that. Now, we can also see the relationship in the lags. You might expect that the quotes don't happen on the same day that the advertisement happened. Maybe it takes 2 or 3 days for that to happen. So for this, it's useful to look at some time series, some ggplots, some scatter plots. I'll put what we want to predict on the y-axis, quotes, And on the x-axis, I'll put TV adverts and use a scatter plot. So on the same day, there seems to be a very strong relationship between these two variables. But what about the day before? Does today's quotes relate to the previous day's advertising? So for this, I can use lag, and you can see it's not nearly as strongly related as before, but I can use geom_smooth method equals lm to see if there's any relationship at all. And you can see that there's a slight upwards relationship between the quotes from today with the advertising that happened yesterday. Or I think this time series is monthly, so the advertising that happened last month. What about if I lag 2 steps back? Now you can see there's barely any relationship, and it's not worth including in our model. If I do 3, we're really not seeing any significant information at all. So when we choose our model, we might like to use model quotes using TV advertisements, but also the last month's advertising as well. Okay, I see a question in the chat here. Does lagging work for irregularly spaced time series data? So the lag operator here doesn't understand time. So it will use the previous observation. If you have yearly observations and then one observation, you skipped a year, it will go back to the last observation you had. So it might be irregular itself. So you do need to be careful when you use the lag operator with irregular data. It will work, but you might not get what you expect. Another question in the chat about registration. We're going to post the registration spreadsheet at the end of this session in about 5 minutes. So you've not missed it. So let's create a model for this. We can use, oh, there's another great question. Is lag equal, is this the same? And that's true. If we look at the documentation for lag, you can see it's the value and the default is k equals 1. So we can set the first parameter bit 1, which matches the default, or 2 or 3 to change the number of steps back we go. Another question a little bit further back about dummy variables. What are we trying to capture? We're trying to capture some special event that might have happened, or some categorical information, like what day is it? Is it Monday, Tuesday, Wednesday? We can use dummy variables to represent what day it is, and consequently that can incorporate seasonality in our model. So dummy variables can capture lots of things. Most often in time series we use seasonality. We capture seasonality using dummy variables, but we can also use it to describe special events. So we can use lags in our model because we might expect it to take some time for the effect to come through. Say you just saw an advertisement on your TV and you now want to get a quote for that product. In this case, this is for insurance. You see an insurance ad. Do you call up the insurance company immediately and say, hi, I want to buy insurance? Maybe not. You might call them up tomorrow, the next day. Including lags allows you to model both the people that call up immediately, which I'll add in the model now. So we'll use TSLM quotes against TV adverts. This coefficient, this regressor will include all the people that answered immediately on the phone. But what about if they answer and call up after seeing an ad yesterday? For this, I can add in the lag of TV adverts. So this is all the people that saw the ad yesterday, or for this data set last month. And that has a relationship with quotes as well, the number of quotes they get. So including lags of regressors as well can be useful for producing predictions if you expect that there's a lagged relationship. And we saw that there was a lagged relationship by comparing quotes with the lag of advertising. You see there's a positive relationship here. So it's worth including in our model. But to make sure it's worth including in a model, it's worth looking at the AICC and the CV statistic. So let's compare a model with and without the lag. Remember, we use the glance function for this. And we can see that the second model here, the one that includes the lag, has a better cross-validation statistic. So the lag improves this model. What about if I add a extra lag? Maybe I add going 2 steps back. So now you can see the adjusted R² has actually decreased and the cross-validation statistic has increased. So we want to minimize these values of AICC and cross-validation statistic, but maximize adjusted R². And you can find the best possible number of lags iteratively. You can look at a plot for the relationship between them, or simply look at the glance for adjusted R² and cross-validation statistic. Now we have a bit of a disagreement here in the output. The adjusted R² says to include lag 1, but the cross-validation statistic says to not include any lags at all. Definitely we don't want to include 2 lags. Both of the models say no to that, and both of the columns say no to that. So you can see lag 0 is strongly related, lag 1 is not really related, it's only slightly related, and lag 2 has no relation at all. So here we try all of the models, and we can look at the AICC and BICC to choose what the best lag order was. This code is a bit advanced. It's using an ARIMA model that we'll be seeing tomorrow, but you can see that ARIMA also works with these regressors, just like we see in regression modeling. There's a question in chat about the cross-validation statistic CV. Do we want smaller or bigger values for this? CV is relating to your error, and you want small errors. So we want the smallest possible CV, which is what we get from our first model, which didn't have any lags. R², we want to be as close to 1 as possible. We want this to be big. And so in this case, the biggest is the second row, which had a single lag. So either 0 or 1 lags will give you a decent model here. They're both good. Okay, so here we estimate a model using advertising and the lag of advertising. This is an ARIMA model, but it's much the same as what we've just done here with LM. And you can see we get our regression model coefficients, which we can use to produce some forecasts. But remember, when we produce forecasts with regressors, it's a bit tricky. We need to provide the future value of the regressors. And here we're just assuming that we're doing 10 advertisements, but this is really useful for your client because they might be able to decide how many advertisements they're going to run based on how many sales they need. This is where scenario forecasting can be really useful if you can control what happens to the regressors. So you can see if we only did 8 advertisements, we have a lot less insurance quotes. But if we only do 6 advertisements, we get a far fewer quotes. So lags are particularly useful if you have leading predictors, something that usually happens after the announcement. So sales might lag the announcement of a policy by a few days, or the number of insurance quotes might lag the number of advertising by a few days as well. Okay, that's all I have for you today. So thank you all so much for coming. I will stick around to answer a few more questions. Please do attend your mentoring sessions. Your mentors are there to help you, and they can also help answer some questions and work through the exercises. In particular, the day 3 exercises are really helpful for explaining each of the models that we've seen today. And for regression, it talks about the knots, if that was a bit confusing for you. And it also helps you with setting up future values for scenario forecasting. So there's some extra information for when you encounter these sorts of errors that we looked at today. I see that Bahman's just put into the chat the attendance spreadsheet, so please click onto that and fill out your attendance for today. And meet with your mentor soon so that you can work through these exercises with them. Thank you very much, and we will see you tomorrow.
There are, I think, 3 questions in the Q&A. I think you have answered one of them at least.
Are there lags in the units of time series? I'm not sure what you mean by that, but usually the units of our lags are the frequency. So remember right at the top of the tibble that we had the 1M for monthly data, 1Y. Whenever you lag, it will usually lag by that frequency. Could we introduce time series models with Bayesian approaches? You can use Bayesian approaches for time series modeling, but it's not something that we're going to cover this week. It's a bit too advanced. Maybe your mentor will be able to discuss this with you, but it's a very different approach from the tools that we have in the Fable software. So it's not something that we're covering this week.
Sorry, just to clarify, I haven't posted the link I posted for attendance has 3 sheets. Day 1 and day 2 is already locked, so you can put your name on day 3. And also the materials for the training is available in this website, so please click on it and then put it somewhere in your browser, bookmark it, so you can find everything there. Recordings are available for each day after the session. We upload them on YouTube and we put them on the website. So there is something here. Someone put an error. Is it? What is this?
Yeah, it says the file is not found for both days.
So which file is it?
Yeah, for the code, I haven't had the chance to
Okay.
fix the links for that. Sorry about that.
Yeah, so
I will get that for you as soon as I can.
Yeah.
Okay, thank you.